We got a great lesson here today because we're going to learn some shortcuts. We're going to learn how to use some postulates and theorems to prove that polygons are congruent, specifically triangles, so we won't have to prove that all the corresponding parts are congruent. So it's going to be great. It's going to give us some shortcuts. So here we go. First of all, we've got a postulate. It's called the side-side-side congruence postulate. And we're going to call that the SSS postulate. That's convenient. And what does that say? It just says if three sides of one triangle are congruent to three sides of a second triangle, then the two triangles are congruent. So if MN is congruent to QR and MP is congruent to QS and NP is congruent to RS, then I know that triangle MNP is congruent to triangle QRS. Okay, next we've got the side-angle-side congruence postulate. Abbreviate that SAS. If two sides and the included angle of one triangle are congruent to two sides and the included angle of a second triangle, then the two triangles are congruent. Well, what do we mean exactly by the included angle? Well, you see, it's the angle that's in between the two sides that are congruent. So you see how angle X here is kind of in between or included. So you could sort of think of those two sides as being the legs of that angle X. The included angle has to be between those two sides that are congruent to the other two sides in the triangle. So if PQ is congruent to WX and angle Q is congruent to angle X, and side QS is congruent to side XY, then we know that triangle PQS is congruent to triangle WXY. See, this is nice. I don't have to find that all the corresponding parts are congruent with these new postulates. All right, then, so we had side angle side there. Now we've got angle side angle. ASA, as you probably would have guessed. And it says if two angles in the included side of one triangle are congruent to two angles in the included side of a second triangle, then the two triangles are congruent. So see here again, AC, this side AC here is included. In other words, it means it's in between the two angles. So if angle A is congruent to angle D, and AC is congruent to DF, that's the included sides, and angle C is congruent to angle F, then I can say that triangle ABC is congruent to triangle DEF. Much nicer than having to show that all the corresponding parts are congruent. Oh, wait, here's another one. Angle, angle, side. Angle, angle, side, AAF. Sorry. Oh, look, that's the only one that's a theorem, right? The others are postulates, postulate, postulate. Yep, AAS is the only one there that's a theorem. And it says if two angles in a non-included side of one triangle are congruent to two angles and the non-included side of a second triangle, then the two triangles are congruent. So there's the non-included side, you see. It's not between the two angles that are congruent, and that's okay because we now have this theorem. So if angle A is congruent to angle D, and angle C is congruent to angle F, and side BC is congruent to side EF, and I can say that triangle ABC is congruent to triangle DEF. And as always, the order that I name those things in does matter. Okay, what you want to be aware of. There are no angle, 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 no angle, 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 or no angle, side, side triangle postulates. Okay? I'm just going to leave that right there with you. You cannot use angle, 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 or angle, side, side, or side, side angle because they do not exist, and those things alone would not be enough information for you to prove that two triangles are congruent. Okay, let's do some examples. Are the triangles below congruent? Justify your answer and write a congruent statement if the triangles are congruent. Well, look, we've got all three sets of corresponding sides here congruent. So yes, these are congruent by side, side, side. Congruence postulate, and I'm going to write the congruent statement. Triangle DEF is congruent to triangle JKL by side, side, side. And when you're writing a proof, you can just put side, side, side. You don't necessarily have to put side, side, side congruence postulate. If you remember that it is a postulate, that's fantastic though. Okay, how about these two? Let's see what we got here. All I really need to know is whether or not angles 1 and 2 are congruent, and they are, right? Because they're vertical angles. So by the vertical angles theorem, angle 1 is congruent to angle 2. Therefore, I can say that triangle STY is congruent to triangle WXY by side angle side, right? Side angle side. Okay, how about these two? Let's see, what have we got here? I got two right triangles, so that much I know. I know that this side here, EG, by the reflexive property, EG is congruent to itself. So let me write that down. By the reflexive property. But that's really all I know. I just have a side and one pair of angles. I don't know that angle F is congruent. If I knew that angle F was congruent to angle H, then that would be angle side. If I knew that angle F EG was congruent to angle HEG, that would be enough, but I don't know any of that, so I can't say that these two are congruent. So I'm just going to say not enough info. Not enough info there. I mean, they might be congruent, but there's not enough information here for me to know. Okay, why don't you pause right here and figure this one out for yourself and then come back and check it. Alrighty, so what we can see here is we've got two angles, and what we got to realize is that this side here, RQ, is shared by both triangles, so we do have congruence there by angle side angle, because this angle is congruent to this angle, and this one is congruent to this one, and the included side is RQ. So we can say that triangle PQR, and remember our vertices have to line up, PQR. So angle P is congruent to angle S. Angle Q, well, I can't call it angle Q. I got to call it angle PQR is congruent to angle SRQ, and so forth. So triangle PQR congruent to triangle SRQ by angle side angle. Okay, I think all we have left is some proofs to practice. I will probably do this first one with you here, and then you're going to pause the video and you're going to take a stab at the next two, and then I'll put them up for you so you can check them. Okay, I'm just going to pause right now and set up my statements and reasons columns so that you don't have to waste your time listening to me do that. So hang on a second and I'll be right back. Okay, here we go. So I've got my first statement written down. Of course, we always put the given first. I always number my steps. So let's see. Remember, what I need to do is they're not giving me this information for no reason. So I've got to figure out what to do with this information that they've given me. WX, so here's WX, just going to highlight it with my pencil. WX is parallel to ZY. Okay, I need to use that information somehow. So what I'm going to do is I'm going to think of WZ here as a transversal, which it is. right? WZ is a transversal. So the fact that these two lines, WX and ZY, are parallel tells me something about some angles. Because you remember all those theorems we had related to parallel lines? Well, one of them was the alternate interior angles theorem, right? So if I look at this angle right here and this angle right here, they're created by those two sets of parallel sides there in that rectangle. Well, I'm saying it's a rectangle. Anyway, I know that those are parallel, therefore those angles that I just marked are alternate interior angles, and I know that they're congruent by the alternate interior angles theorem. So I'm just going to let that be my next step. So I'm going to say angle XWZ is congruent to angle, let's see, YZW. And what we say? We know that because of the alternate interior angles theorem. Okay, so look what we've got. We've got a side, we've got an angle. So what if we say that this side here, which we also used as a transversal, what if we say that that is congruent to itself? What if, because that's true, so that's WZ, right? WZ is congruent to itself by the reflexive property of congruence. So that gets it for us, right? I'm just going to put a little squiggly there. So what I can see is that I've got those two triangles congruent by side angle side. So triangle WXZ is congruent to triangle ZYW by side angle side. There we go. Simple as that. Sometimes as you go forward, I don't know, you might see this somewhere in computer science. Sometimes when you're to the end of a proof, you'll see somebody write this statement. Perhaps I've mentioned it in an earlier lesson. I can't remember. QED, I don't know exactly what that stands for, but I do know that it means the end when it comes to this proof. So that's just a little tidbit for you. Okay. Why don't I let you pause here, and when you come back, you're going to check. Now, don't just fill it. Don't just come back and fill it in. I really want you to pause here and try to do these two proofs, and I'm going to fill them in, and you can come back and check your work. So this proof here isn't all that different from the one we just did. We write down our given statements, and then what we can see, because WY is parallel to XZ, is that again, if we let WZ be a transversal here, then we've got alternate interior angles right here and right here. So you can see in step 2, I said that those two are congruent by the alternate interior angles theorem. And then once again, these two triangles share this side. So I tend to put a squiggly there when they share a side, and I say it's congruent to itself by the reflexive property of congruence. Therefore, I know those two triangles are congruent to each other by angle, angle, side. And finally, I didn't quite finish this one because I want you guys to see if you can fill in the missing pieces here. So I'm just going to leave this as it is. Try to fill in the missing parts and make sure to remind me to go over it with you at the beginning of class. That's all. Put in your summary, and we'll see you next time.